Well, here we are one more time again. It is the physics video lecture, Psci 168, video lecture 39. This is a very short announcement concerning the final exam. So I'll begin by writing the time of the exam up here on the board. Final exam, Monday, May 10th. Monday, May 10th, and the time is 11 o'clock to 1 o'clock. So I will send the exam out some few minutes before this, and we'll try to get them in on time. Okay. So having said that, we'll just spend a few minutes talking about the problems that will be on that exam. Once again, Monday, May 10th, 11 to 1. Same as before, I email it to you. You guys send me images back, email images back to me. Okay, so here's the review. The first couple of problems, since it's cumulative, they cover topics that we've had on the first midterm exam. So we're talking force, work, energy, conservation of energy. You want to use the definitions that we discussed in class. Okay, I can easily tell if you just got it off of the internet, and it's probably not quite right. Okay, so we have lots of examples and discussion of these concepts here. I want you to be able to give examples and use, for example, weight, M times G, right? We know about G now, so that's a force. And for example, you could say 80 kilograms times 9.8 meters per second squared, multiply it out, and then tell me that the units are in newtons. So you want to be able to do that. If you're talking about energy, potential energy, M times G times H, and again, give an example, a concrete example. For example, this could be my weight, except I weigh a bit more than that. Okay. An example, we've used this formula for many things, the grandfather clock all the way to the hydropower problem. And the law of conservation of energy, you probably want to be able to state as well. So you should have all that material in your notes and be prepared to deliver I'll maybe formulate something special I want, but it's in terms of these concepts here. The next thing is the hydropower problem. So just for general principles, you want to be able to give the labeled sketch etc., the formulas, and be prepared to solve the problem using the formulas. So yeah, go back into that material. For example, we've got the potential energy, which I'm going to call capital W this time, mgh, and then we've got the power, m over t times g times h, and then we have energy equals power times time, just like power equals energy divided by time, and the units here, the joule, the watt, etc. So I'll give a problem and the volume of a reservoir, very similar to what we had last time. But we also want to be able to put it into context with regards to the other energy forms that are involved. You've got your pump storage problem, the water cycle, solar energy. Solar energy is actually playing into the hydropower problem. So yeah, I'll give you a hydropower problem. Then we have heat engines. So we had a big section on heat engines. And I'll just write here the definition, examples, the schematic diagram, efficiency formulas, and you'll remember we had to know about Kelvin degrees here. So efficiency, anything else there? That's a Carnot efficiency, right? Carnot 1 minus Tc over Th. So yeah, many of these things. And I may also try to tie it into one of the more exotic ideas like the solar chimney, solar thermal ideas and stuff like that. So what do I have on point 4 here? Yes. So this would be a continuation of the heat engines and the thermal physics in general. The solar constant. So I mean these 1,340 watts per square meter. So the solar constant, but there's a whole lot of thermal physics in order to even define this, the route we took. There are different ways to get the solar constant. We've just talked about heating up some water in the sunlight. Okay. So the discussion of the solar constant really allows you to go back to your thermal physics. Should I write that here? I'll say plus thermal physics. So yeah, both of these topics are very rich in the thermal physics aspects, but they have ties into other things. Because after all, the solar radiation is a form of electromagnetic energy, and yet at the same time, it's a heat transfer mechanism. So okay, that's a good couple of problems. And then finally, you'll see how this just covers the whole world of energy as we've studied it. Well, I'll ask you to answer something about electricity. Okay. So here we're talking about the formulas that just involve basic circuitry and household power usage. So yeah, then you're going to want to remember formulas like Ohm's law, power formula I delta V, primarily. Then of course you're going to want to remember, I have it up there, yeah, relation between energy, power, and time. So the kilowatt hour definition of the kilowatt hour, we've learned it before we learned anything about electricity. Good to know here. And potentially also the tie-in to hydropower, because a certain amount of potential energy represents a certain number of kilowatt hours. Okay. And here we're also talking about the energy and the power used by an appliance. Multiply that by time, and you get the energy used by the appliance. So yeah, if you take this and consider what we had on the first exam, where we were even talking about satellite orbits and things like that, you have a pretty complete view of and practical understanding of energy, which is what we set out to do. Good, so once again, before I end this, our final exam, Monday, May 10th, 11 o'clock to 1 o'clock. If you have any questions, let me know, send me an email, but otherwise, see you guys then.